Artificial aerosols, microscopic particles capable of reflecting solar radiation in the atmosphere, can be sprayed at high altitudes to achieve rapid cooling effects. However, this counterproductive human intervention, while temporarily reducing atmospheric temperatures, actually accelerates ocean warming, leading to severe disasters in fisheries. As a result, numerous marine species including shellfish, seabirds, lobsters, cod, sea lions, seals, and whales have perished. Pathways of artificial aerosols. Once introduced into the atmosphere, artificial aerosols typically undergo 3 stages. 1. Slow movement in the stratosphere. 2. Rapid descent in the troposphere. 3. Floating and sinking in the ocean. The duration of these stages varies based on local air currents, ocean currents, temperature, season, and geography. Regardless of the time involved, the aerosol's interaction with solar radiation, reflecting, refracting, scattering, and backscattering, creates varying scales of radiant heat zones across the atmosphere, surface water, and underwater. Dual-layer radiant heat effect. Upon entering the ocean, artificial aerosols float on the surface for a period before sinking. As they move with ocean currents, they either disperse or accumulate. When aerosol particles reach a certain density on the surface, the intense reflection of solar radiation generates a heat radiance that elevates sea surface temperatures. Some of the penetrating sunlight interacts with underwater aerosol particles and lower-level water surfaces in complex patterns of reflection and refraction. This dual-layer radiant heat effect traps the ocean on a one-way path to irreversible warming. Ocean hotspots. The cancer within the sea. Artificial aerosols are not the primary culprits behind marine disasters but are rather the result of poorly considered actions within net-zero emissions projects, inadvertently accelerating the warming of oceanic pathways. Today's oceans, akin to the Earth's dump sites, receive all toxic waste from the atmosphere, land, and rivers. The increasingly hot, acidic, and oxygen-deprived waters catalyze unpredictable chemical reactions, devouring life around them like cancer cells, spreading rapidly and visibly even from satellite imagery. These are the ocean hotspots. Emergency ocean aid. Hydrogen and oxygen needed. Facing unprecedented levels of pollution, the ailing ocean has lost its natural purifying ability and is in desperate need of rescue. Addressing each pollutant individually might seem too slow and resource-intensive without guaranteeing results. A more viable approach would focus on reigniting the ocean's self-healing capabilities. Just as a healthy human body detoxifies, purifies, and regenerates, a high concentration of oxygen and hydrogen could strengthen marine life functions and reboot the ecosystem, urgently necessitating CPR for the dying ocean. A new dawn with matter-energy conversion technology. Deoxygenation, hydrogen deficiency, acidification, and high temperatures laden with toxins create a domino effect, propelling us toward a climatic tipping point. Preventing the continuous collapse of marine ecosystems hinges on 2 crucial factors: removing toxins and increasing the concentration of oxygen and hydrogen in seawater. Should a novel technology capable of restructuring molecular pollutants to convert them into hydrogen and oxygen emerge, it could simultaneously address these critical challenges, shining a ray of hope on marine pollution control. CRCS Marine Carbon Pollution Solution. Our strategic approach to technology employs removal, conversion, and reduction. CRCS represents a groundbreaking negative carbon technology, directly converting CO2 into hydroxyl ions without the need for capture, storage, or chemical transformation. It processes gases, soils, and water bodies, rivers, lakes, dams, and oceans, boasting extensive scalability, high efficiency, low carbon emissions, low material use, no pollutants, and a high recovery rate. To effectively address these challenges, which cover 70% of the Earth's surface, a synchronized implementation of 3 types of installation strategies is essential: fixed site, liquid type, and put-in. 1. Fixed site construction. The blueprint is to deploy CRCS systems along oceanic circulation paths, performing CO2 conversion within effective ranges at fixed points, utilizing natural conveyors, currents, to distribute healthy seawater to surrounding areas. Connecting points into lines and lines into rings form the optimal broad-spectrum CO2 conversion solution. Requirements: internal space larger than 200 times 200 times 180 centimeters, 110 V power, simple ventilation according to ambient temperature, and location within 700 meters from the sea. 2. Liquid-type construction. CRCS systems are installed on various medium to large watercraft, including yachts, cruise ships, ocean fishing vessels, cargo ships, or oil platforms, forming a large-scale CO2 conversion network along their routes. This complements the fixed-site ring model for a comprehensive marine carbon pollution conversion solution. Requirements: adaptation to the available space on the watercraft, ranging from 100 times 100 times 100 centimeters to a 20-foot container, 110 V power requirement, simple air conditioning, with ocean-going cargo ships accommodating systems in containers or holds. 3. Put in. The CRCS zero electricity system is deployed into the ocean to create a checkerboard-patterned resonant effect for CO2e removal and conversion. This system operates without electricity and is capable of functioning in soil and seawater for over 100 years. The deployment depths range from 100 meters to 1,200 meters, with flexibility according to local conditions. The optimal seabed depth for deployment is 1,200 meters, where increasing the density of deployment significantly enhances the carbon pollution removal rate and helps balance the pH levels of seawater. Triple overlay effect. Utilizing a combination of fixed, mobile, and deployment frameworks allows for the synchronous treatment of carbon in the sky, soil, and ocean. This integrated approach leverages ocean currents, shipping routes, and a checkerboard network of bases to create the most comprehensive marine carbon removal and conversion model. The torus field, torus, at the core of this model indicates the matter-energy transmutation pathways and the directional orientation of the field, extending longitudinally, expanding laterally, and radiating outwardly. The effective range of a single system varies with the resonance rates of gases, water, and soil, with effective heights of 7 to 14 kilometers and diameters of 20 to 35 kilometers. Installation scale. The scale of removal and conversion is directly proportional to the number of systems installed. For example, in the South Atlantic, using the minimum standard would require 36 fixed-site installations along the coast, 20 to 30 cargo ships on fixed routes for mobile installations, and 70 to 80 CRCS units for ocean deployment. If resource allocation is a consideration, prioritizing the ocean deployment model could be optimal. Annual effectiveness estimates. For the South Atlantic removal and conversion model, the expected outcomes include a 45 to 55% CO2e removal rate, a 60 to 70% increase in hydroxyl rate, and a 60 to 70% acidity balance rate. These figures are based on calculations by the EQT Marine Carbon Removal Research Team, which is open to conducting physical tests with third-party professional organizations. The health of the oceans directly impacts the Earth's habitability. We must exert our greatest efforts before reaching the critical threshold of extreme climate change, with a key focus on the oceans.